So let's continue with our Bresenhams algorithm code. Now on the left here we have the code here which we've seen in the last video, and on the right we have the Python, which is what we want to generate in our assembly language. So we've seen the first little section here down to here, okay, which generates the position relative to the center of the screen. Now the next thing we want to do is we want to be able to work with our variables locally here within our subroutine, and at the very end we don't want the global variable to change. We're going to leave those exactly as they are, so we just work within our subroutine. So it means we're going to have to make potentially a couple of copies of the values. So the first thing we want to do here is we want to work out our dx and our dy. We generate those by finding the absolute value of our x2 minus our x1. So what we can do is we can copy our x1, x2, y1, y2, and that's the move. So we can move those into another memory location. So now we've got in effect two copies. We've got the copy in y2 temp, and now a y2 local copy as well. Now we're going to go through the subtraction, so we subtract the values here. So this is going to be the final x1 local copy will be equal to x2 temp minus x1 local copy. Okay, so this is just subtracting those two values, and again we subtract the y values here as well. And then we're going to use our absolute value algorithm, which we generated in a previous video when we looked at starting a mathematics library. So the whole point here is that you can generate a complex piece of code by breaking it down into individual subroutines. So we're going to write a code for our Bresenhams algorithm. We're going to write a code to draw a line, and that code is going to call Bresenhams algorithm. But within Bresenhams algorithm is going to call another piece of code which we generated, which is the mathematical code for working out the absolute value. Okay, so we can generate nice complex bits of code by building up this hierarchy of subroutines within the ROM, and we'll look more into this in the next course. Well, let's crack on and get this done. So we've subtracted these values off. What we can do is we can push this x1 local copy, okay, which is just the value x2 minus x1, into our maths function. Okay, so it jumps to subroutine math ABS. Of course, the math subroutine math ABS is defined down here. So we can see here it's got the math ABS, and it's a position in memory. So we just do the EQU and we just give it a number. Okay, so it just replaces this here with the 0 cross 350. Now again, whenever we go and do the next course, it'll all be about organising the ROM. So potentially we might move some of these things round about, okay, in order to get it sitting in a more kind of organised and efficient manner. But we'll get to that on the next course. So we push it in, it jumps to the subroutine, and then it pops the value back out. So we can pop it straight back out into dx. And we can do the exact same thing with the y value. We can push the local y copy, jump to the subroutine, and we can pop the value back straight into the dy. So that's us generated our dx and our dy. So that's a good start. Now the next thing we want to do is work through the if statement. So the first part of the if statement says if steep, then we're going to swap these round about. Okay, so we have to do a test. So we can compare the dy and dx. Okay, now if the dy is greater than dx, it means that the y component in the line is higher than the x component. So it means it's going to be a steep line. That is, it's going to be a gradient which is greater than 1. Okay, so we can do the steep part here. Okay, so this is the swap section here. Now, if it isn't steep, it will jump if a is less than or equal to not steep. So n steep just means not steep. So it would jump down to this part of the code here. So this part of the code here would just be the next if statement. Okay, so if it is steep, it will go in and do this, and then it will go and do this. But if it isn't steep, it misses out this section and just jumps straight to that section there. Okay, so now we'll just go through it line by line. Okay, so this little section here is if it's steep. If it's steep, it swaps the x1 and the y1 values. Okay, so the x1 becomes y1, the y1 becomes x1, the x2 becomes x1, and the y2 becomes y1. The dy becomes the dx, and the dx becomes the dy. So we just need to go through that swapping process. So one thing I'm going to do first of all is I'm going to make a little note that that is indeed actually steep. Okay, so I've set aside a memory location called steep test, and if it goes into this little bit of the routine, it just sets that to a value of 1. So we know we can always go and test that memory location whenever we require to work out whether it's steep or not. We don't need to go through any sort of test again, any comparison. We can just jump in there and we'll be able to tell. Okay, so if it is steep, that will be set to 1. If it isn't steep, it will be set to 0. So all we're going to do is swap these round about, and the swapping process is quite simple. We take our x1 temp, we put it into R0, we get our y1 temp, we put it into R1, and then so we load them in from the memory locations into R0, and then we store them in the other memory location from R0 to R1. So you can see this swapping round. So the x1 temp is in R0, and R0 goes to the y1 temp. The y1 temp is in R1, and that y1 temp goes to R0. So we'll swap these round. Now we do the exact same thing here. We swap them round for the y's, and we do the exact same thing here. We swap them round for the dx and the dy. So that's us covered this little section here. Now we jump down onto the next if statement. So the next if statement is here. If x1 is greater than x2, then we swap x1 and x2 round about, and we swap y1 and y2 round about. So again, we come in and we do a comparison. So the comparison is x1 temp and x2 temp. And if the value here is greater than, then we jump in and do this. If it isn't greater than, then we jump down here to the next line here. Okay, so if it isn't, then it jumps down to n steep a, so it'll jump down to this point here. Okay, and then it'll just do, it won't do this here, it'll just go straight into this if statement. Okay, so let's talk our way through this statement here. Okay, so we're working through here, and again all we're doing is swapping the x's and the y's. So we can come in and x1 temp goes into R0 and x2 temp goes into R1, and then we swap them round about by storing them in the opposite way. And we do the exact same thing with the y1. The y1 and the y2 come in to the registers, and then we store them in memory in the opposite location, the opposite way. So that's us worked through this here. So now we're on to the next if statement, which is the if y1 is less than y2. So this is an if else. So if this statement is true, it goes in and does this here, y step is equal to 1, and then it misses out this line here and goes straight to here. Now if this statement is false, it doesn't do the y step equals 1, it does the y step is equal to -1, and then it jumps down to the next line of code, and you can see that happening here. So we do the comparison here for the y1 temp and y2, so that's this comparison. Now if the value is greater than or equal to, it jumps down to the else, so it'll jump down to this value here and put it in as -1, and if it isn't, then it will do the next line here, which puts the value 1 into the y step, okay? And then we don't want to do this line here, so it just jumps over to the next line, which we just call next, which in effect is this point here, okay? So that is the if-else statement, okay? And it puts the value for our p as the value, it puts the value sort of the y step as plus and -1. Okay, so we're doing quite well. We've got quite a way through the code quite quickly. So now we're at this point here, which is called next, and that is this point here. Now, of course, I'm not a coder. It's not really necessarily my profession. You know, mathematics is my thing. But so it means that if you're looking at this code and thinking, I could write this a little bit better, a little bit neater, I could use better different variable names and different names for the labels, then by all means go ahead and do that and generate your own code the way that you like it generated. Okay, so we're going to head down in here and we need to generate this p is equal to 2 times dy minus dx. Okay, so and you can see here we've generated it here, and I won't talk through it in detail, but we load the dy into R0, we load the dx into R1. We need to get 2 times the value of our dx. Now, the best and easiest way to get a value of times 2 is to just use the shift. So if we shift to the right in a binary system, it's equivalent to multiplying by 2. So all we do is we shift to the left, okay, so it shifts it further up, okay. So we shift by a value of 1, okay, and that is equivalent to multiplying by 2, and we save the value in R0. And then we do the subtraction, so we take the original value R0 minus the new value R1, and we place the answer in register R1. So we do the subtraction and we store the value in the position P. Okay, so we've got this 2 times dy minus dx, and then we do this point here. We have y is equal to y1, so we move y1 temp into a new variable called y. Okay, so now the last part of our code here is probably the most awkward part to explain. So let's work through. It's our for loop. Okay, now in Python we don't have the return statement, so we don't have a for and a next. So because the language is an indented language, it knows it has to return whenever it finds a line which sits it's unindented. Okay, but anyway, if you code and you know Python, you probably know a lot more about this than I do. Okay, so we've got our for next loop here, and what we're going to do is we are actually going to enter straight into the for next loop here. You won't see there's nothing here that tells you it's a for next loop. So we're going to enter in, and then we're going to make the changes for these x1 and x2 values at the bottom, and then jump back up and then continually running through it. Okay, so the first thing that we're having to do here that you can actually see in the code is we're going to move a value of the x1 temp into x. Okay, so this is the same equivalence as here. Okay, you don't see it in the code here because it's dealt with within this for statement, but it's not dealt with within the for statement here within our assembly language. You have to physically do it. Okay, so we've got this move x1 temp into the value of our x. So in effect, you're initializing your x and initializing your y positions. Now we have to go through this test, and again it's if steep. Now rather than going through the test, all we need to do is make the comparison of the value of 1 with the memory location called steep test. So remember, that was the reason why up here I generated the steep test up here. So I put 1 in whenever it's a value of steep. So we can test that value here. So compare steep test, and it says if it's steep, then what it does is it prints out the values, but it prints them out round the other way. Okay, you can see here that the X position gets printed as a Y and the Y position gets printed as an X, so they're swapped round about whenever it's steep. Okay, so we do that here. Now this case here, if it isn't steep, it jumps to the else. Okay, and we know it's not steep, so it prints out the values just normally, the X and the Y. Okay, there's no swapping. So it's really another if-else statement. So we jump in here and we can jump if it's not equal, okay, to the shallow, in which case it goes down here. If not, it's a steep and it's going to go through this section here. So this is a section where we're going to print the values out to the screen. So what we're going to do is we're going to, in order to print the values out to the screen, we're going to have an X and our Y value. So our X value is a 16-bit and the Y value is 16-bit, but we're only actually using the least significant 8 bits for each of them, because it's just a number between 0 and 256. Okay, so in our instance here, it will actually be a number between -128 and +128. Okay, so what we can do is we can take our value here, but we can load our X value into register R2, and then we can shift that X value 8 positions along. Okay, so it becomes the most significant 8 bits, and then we can get the Y value put into R3, and then we can OR both of them together, so we get both the X and the Y positions within 116-bit. Okay, a 1 byte or a 16-bit bit of memory. So we're going to have the X position at the most significant 8 bits and the Y position in the least significant 8 bits. And then we're able to go through the process of printing out. So what we'll do is we'll load the colour into R5, and again we've got the colour down here. You can see the colours define a storage position of 1 byte. So we shift the colour into R5 and we're ready to do the pixel command. So the pixel, it picks out the graphics card, which is F5. So again, I've just called that graphic card, and you can see the graphic card is down here. Okay, F5. And the R5 is the colour and the R3 is the position. Okay, so that should plot that point out on the screen, and then it jumps to the exit A. So it jumps over this else statement to the next if else. So it jumps over to this point here. Now the other one is the positions that they don't get swapped round about. So we do the same thing again. Now if the line is a less than gradient 1, we'll load, in this instance, the Y2 into R2. We shift the Y value over to the most significant bit, and we load the X value into R3, and then we OR them together. So now the X value is the least significant bit and the Y value is the most significant bit, so that whenever it prints out here, it will then print it out as XY as opposed to YX. Okay, so that's the first part of the for statement. We get into the next part of the for statement here, and we just generate these two. So it does a test here. It compares 0 to the value of P. Okay, so we're just checking to see whether the value for P is less than 0. If it's less than 0, we do this. If it's not less than 0, we do this here. Okay, so in this instance here, if it's less than 0, then we're going to work out this P plus 2 times dy. And again, we do that by loading dy into R2. We can shift the value of y by one position to the left, so it multiplies it by 2. We load p into R3, and then we can add both of them together, and then we can store the final value back in p. Okay, so now we've got p plus 2 times dy, and then we can exit to position b. So we jump over this else statement to the end, so we jump over to that point there. Now the other one here is a bit more involved. It's p plus 2 times dy minus 2 times dx. Okay, so we can get our 2 times dy again by shifting to the left. Okay, and then we can get our 2 times dx again shifting by the left. We can do a subtraction, and then we can store it back in p. Okay, so that gives us this line here, and then we can do our y is equal plus equals y step. So it's y is equal to y plus y step, and again we just do the same by putting the y into register R2, the y step into register R3, we add the two together and we store the result R3 of register R3 into y. So this has done this here, so that's us done the vast majority of the code. But we still have to implement this test here for x in the range x1 to x2 plus 1. Okay, now in this instance here we don't need to bother doing the plus 1 bit, because the way we've set this out is it actually runs through the first one and then does the comparison and then jumps up again and goes through the for loop until it gets to the end. Okay, so we don't need to do this plus 1 thing here. So what we're going to do is we're going to take the value of our x2 temp and put it in the index register. We're going to take our value of x1 temp and it's in register R4. We do our comparison, so this is in effect doing a comparison here. We're testing x in the range x1 to x2. Okay, now if the comparison, if the value for x is less, x1 here is less than x2, then we want it to jump back up to the beginning of the for next loop. Okay, so in this case here we do the test and it jumps if the value is equal, so that is if it's went through all of the values for the for next loop and the x1 value is equal to the x2 value, it jumps to the end of the code, which is called ret. Okay, so the ret goes down here and it returns in that case point there, it just jumps back out of the routine, but we'll get to that just in a second. So in this instance here, if it isn't x1 is still less than x2, we're still in the for loop, we need to jump back up to the beginning of that for loop. Then what we can do is we can increment the value of our x1 TMP. We have to have it in brackets because we're incrementing the content of the memory location. Okay, so the memory location x1 temp, we're not adding, remember the x1 temp is a variable and it's the x1 temp represents the variable always is represented by a memory location, not the value within the memory location. So we put the brackets around to tell it that we want to increment the actual value in the memory. So we increment that x1, so we've moved along 1 and we're ready to start the value again. So x1 gets added on a value of 1, and then we jump back up to the beginning of our for next loop, which is the jump up to the action. So it jumps all the way back up here to action and runs through the same thing again. And it keeps running through until our x1 is equal to our x2, in which case we jump to the return address. Now again, we jump to the contents of the memory location return address, and the contents is going to contain the position that we go back to within our calling function. Okay, now I don't know if I've got our calling function up here. Oh yeah, I've got the calling function here. So it's going to jump back up and return to the point just after the position it was called from. So it was called from this point here, and it'll jump up to the next line, which is end, and bang, that's us finished, and that's it ended, and that's it drawn out the line using Bresenhams' algorithm. So there's a lot in that code, and it's a nice piece of code to finish the course off on. So I think if you've got this far, and if you've done the first course and the second course, then you really should give yourself a pat on the back. If you think about where you started in the first course with an AND gate and an OR gate and just some basic gates and some a little bit of Boolean logic, and we've taken that and we've built up an entire system here, and we're in a position now where we've got the actual design for our CPU. The physical design is really quite nailed down. And in the next course, what we want to do is develop on this. And the first two courses were really looking at architecture and generating an architecture that we can build something on. So now the architecture's fixed, or relatively fixed. We will make small changes, but now it's relatively fixed. We can start doing the organization phase. So we can organize all of the routines within the ROM, and we organize how the ROM and the RAM talk to each other, and how we position all of our subroutines within that ROM, and what subroutines we want. Okay, so we're going to look at that in the next course. Lots of stuff still we can do. We can still add in our floating point unit, and we can look at the a floating point library. We might get to that in the next course. We'll just have to see how it goes. And we can also design in a Cordic algorithm. We could design the Cordic algorithm in, we could code it in and put it into the ROM, and we can run it as a program within ROM, or we could actually build a physical implementation of the Cordic algorithm within the actual CPU. We could do both of them. We could test them out and see which one runs the fastest. So there's also the option, but we probably won't get onto it in the next course, but we'll see, of building in a pipelined architecture. So we could start off with maybe an architecture of a 3-level pipelined architecture, and move all the way up to maybe a 9 leveled pipelined architecture. But we're getting way ahead of ourselves now. I'm just trying to put out the fact that we've got masses of stuff that we can still do. But don't forget that you've come this far in the course, and give yourself a good pat on the back for getting here. So thank you for listening. I'll get you on the next video. Goodbye.